Hello again. Apparently in the last video when I was talking about a moving observer, I received a phone call and it stopped the video and I didn't note it. So let's try this again with the Doppler effect for a moving observer, right? Still the same result is going to come out here, that for when the observer is moving towards the source, that the observer is going to notice a higher frequency than what the source is putting out. And when the observer is moving away from the source, the observer experiences a lower frequency than what the source is putting out. But let's just talk about why, as I said in the videos before, the screencast before, what went on there. So I'm going to draw myself. Here we go. So if I'm tapping there, these waves are traveling outwards from the source, and I can throw in some rays perpendicular to the wavefronts there, right? And let's say I had an observer here, okay? And that observer is just sitting there, and here the source is giving out waves, and the observer is receiving the waves such that what the frequency of the source is what the frequency that the observer has, as long as the observer is stationary. But if this observer was to move towards the source, what they would be doing is shortening the time period between when they receive each wavefront. Because right now when they're standing still, the wavefront takes a little bit of time to get to them, and the next one takes the same amount of time and the same amount of time because the wavelengths are identical. But if the observer is moving towards the source, it takes less time to encounter the next wavefront, because it's not just that the observer's waiting for the wave to cover the distance, the observer's also covering part of that distance. And so that's the reason there. Now, if our observer, say, is over here or over here, it doesn't really matter, and is moving away from the source, kind of the same argument, but in the reverse. So if they were just staying still, they would be getting a certain number of waves per unit time as the waves traveled out, and it takes a certain amount of time, that period, for the wave to get to our observer. But if the observer is moving away, not only does that wavefront have to travel an entire wavelength to get to here and another wavelength to get to here, then the wavefront would also have to travel the distance that the observer traveled during that time period, such that it extends the period, right? And therefore lowers the frequency. And that's why a moving observer away from a source experiences a lower frequency than what the observer is putting out. Now, an interesting fact here, you might be thinking, can you outrun the wave? Well, actually, that's a funny thing, because if the observer goes exactly the same speed at which the wave is traveling, then yes, the observer will not experience any waves, because they will always be moving relative, or not moving relative to the wave pattern, and therefore they would see the crest and see the crest. If they were on the trough here, they would just be existing in the trough as they went out with the wave. But if the observer is actually moving faster than what the wave is moving out, they would experience the wave, because they would encounter the wavefront in front of them, assuming they had started at rest and the wave sort of passed them by to begin with. So it's only if the observer is moving exactly the same as the wave speed would they not experience any waves. So that's the Doppler effect. Just to summarize, the observer observes a different frequency than what the source is emitting, because either the source is moving relative to the medium of transport and distorting the wave pattern, or the observer is moving relative to the medium of transport and encountering more waves per unit time or fewer waves per unit time than they would if they were staying at rest.